So this is going to be an example problem where we're going to use multiple linear regression. We're going to have two continuous numerical variables as explanatory variables and also a binary categorical variable. So we'll look at how to interpret our table of results, our coefficients with the standard error. We'll do an F-test, but then we'll also interpret those individual coefficients with a T-test, look at their confidence intervals, and finally we'll also look at the coefficient of determination R squared and the adjusted R squared. So let's have a look at this problem. It's going to be a multiple linear regression problem, meaning that we have more than a single explanatory variable. And we have three explanatory variables in this problem: age, diastolic blood pressure, and a specific kind of diet. And this diet's going to be a binary explanatory variable. And our response variable is this low density lipoprotein. So very simple, unrealistic, almost little problem. Our first model, though, is only going to have these two, age and diastolic blood pressure. Both of them are continuous numerical variables. So they're going to be the only two explanatory variables. And then in a follow-up question, we'll add this categorical variable as an explanatory variable. So let's have a look at our first problem. So we're only using age and diastolic blood pressure. They are clearly both continuous numerical variables. Those are two explanatory variables. Our response variable, or our outcome variable, our dependent variable, so many synonyms for the same thing, that is also a continuous numerical variable, making this a linear regression problem. And we are imagining that the model's already been created, and this is a summary of our model. We see the intercept, we see the age, and we see the diastolic blood pressure. Those are going to give us the three parameters of our model, and those are called coefficients by some computer languages. And we see they're negative 45.5495, negative 0.33, etc. And then for each of these coefficients, we also see the standard error of those values. So what I want you to remember, of course, is that this is beta sub 0 hat, the estimate of that intercept. And this is beta sub 1 hat, and that is beta sub 2 hat. And so these are the values that we see here in the column that gives us our coefficients. And there's the standard error. And we do remember, if you take this coefficient estimate divided by its standard error, then you get a t-statistic. So that's good. We also see a sum of squares, a total sum of squares. And if we do want to remember those, let's put those in green. Just as a reminder of where these things come from, that's the sum, I equals 1 to n. So that's going to be all the values. And that's going to be the difference between every value. So I'm going to say little y sub I and its mean, and square all of those differences. So that gives us an idea of the total variability in y. How does every value in y, it's a continuous numerical variable, it's just a column in a spreadsheet, how does every value differ from its mean? You square all of those, you add over all of them, you get the total sum of squares. The sum of squares due to the regression, remember, that is going to be the difference, I equals 1 to n, of what my model predicts, so put a little hat on, for the explanatory variable minus the mean for that variable in the data set. And then the sum of squares due to the residual, or the error, that's going to be the sum, I equals 1 to n, of what my model predicts for that value and for that specific observation and what that observation really is. And we square all of those. And we see those values. And then in the problem, we were also told that there were 100 subjects in our data set. And so the first question is to do an F-test, just to see if this model as a whole is a significant model. And under a null hypothesis that none of these explanatory variables are linearly associated with the response variable, and the alternative hypothesis that at least one of them is. So can we do this test? Yes, let's start with step number 0. So for step number 0, we have all the summaries that we need, and we actually have everything that we need. We might just have to calculate the degrees of freedom. Let's do that right now. And so let's get our green pen. So remember the numerator degree of freedom, that's going to be nu sub 1, that equals k minus 1, where k is the number of parameters in our model, and we clearly see there's 1, 2, 3 parameters. And then the denominator degree of freedom, that's going to be how many observations we have minus how many parameters in our model. So in this instance, this one's going to be quite easy. We have 1, 2, 3. So this is going to be nu sub 1, that is going to equal 3 minus 1, which is 2. And for the denominator degree of freedom, we're going to have 100 minus 3, that equals 97. So that's what we're going to need. So I'll omit step 0. We've got all the information we want. In step number 1, we just want to know, what are the population parameters that we want. And the population parameters, you can describe that in various ways, but the easiest way for us to think just technically about this is beta sub 1 and beta sub 2. Those are the two population parameters, and we're saying that at least one of them are linearly associated. So you might write something like beta sub 1, and beta sub 2, and you have to describe what beta sub 1 and beta sub 2 is. And remember, we will get to interpret them, but for every 1 unit increase in this explanatory variable, by how much does the mean change for this variable after adjusting for all the other variables. So you can certainly write those out. Let's go to step number 2, which is important for us here in this problem really. The null hypothesis, we're going to say at none of the, forgive that spelling, variables are associated or are linearly, we should say linearly associated. And we're going to say the alternative hypothesis, at least one. I'm just going to say dot, dot, dot. To save you some time, at least one of the explanatory variables is linearly associated with the response variable. So the way that we think about this is, under the null hypothesis, this is not a good model. That using age and diastolic blood pressure to estimate a value for the low density lipoprotein is not a good model. Alternative hypothesis, it is a good model. And I tend to like to think of it in terms of those because it explains more about what we are trying to achieve. Now in step 3, now let's imagine that our problem stated that we should use an alpha value of 0.05 or 0.05. In step number 4, we're going to use an F-test. So what do we use for this F-test? Well, there's various things that we don't go into in the introductory course on biostatistics. What we really want now is just for there to be independence between all our 100 observations. Importantly, we would also want there not to be multicollinearity between the explanatory variables and various other things, as I say, that we do not discuss in an introductory course. And we can assume just that the assumptions are met for the use of this F-test. And we need to know what the test statistic is for such a test, for such a statistic. Well, we're going to calculate in the end an F statistic. And that F statistic, we're going to calculate that by saying it's the SSR, the sum of squares due to the regression, divided by the numerator degrees of freedom. All of that divided by the sum of squares due to the residual or error, divided by the denominator degree of freedom. And this is going to follow the F distribution, and it is on a numerator degree of freedom and a denominator degree of freedom under the null hypothesis. So if the null hypothesis was true, this is the distribution that we'll see in all F values if we to repeatedly take from a population in which these two, none of them are linearly associated with the low density lipoprotein. So let's go to step number 5. We actually want to calculate our F statistic. So to calculate our F statistic, we have the SSR, it's right there. It's 6550.265 divided by nu sub 1, we have that's 2. Divided by the SSE, we have the SSE right there, 3246.967, divided by nu sub 2, and we have that's 97. So if you plug that into your calculator, I get about, and see if you get the same, 97, which is a very big number, 97.84, round about there. So that's a very big F statistic from our data. In step number 6, we just want to know a critical value for this. So we want an F value, and we want that on, specifically, we want that on 2, 97 degrees of freedom, 1 minus alpha, 1 minus 0.05. So if you were to use software to calculate this specific critical value, you can do that. I get a critical value of 3.090. And clearly we have that F is much bigger than this critical value. F is much bigger than this critical value, and so we're going to reject the null hypothesis, reject the null, and maybe I'll just squeeze it into the bottom here, accept the alternative hypothesis. So we can write a test conclusion. In step number 7, I'll write the conclusion, and then we'll just forward a little bit. So I've written there's enough evidence in the data at the 5% level of significance to show that at least one of the explanatory variables is linearly associated with the response variable. The way that I like to think about it, though, in creating some words for a report or paper, is just to think that using those two explanatory variables, that that is a good model to explain this variability that we see in our response variable. And so the next step that we would then go is just to look at these individual explanatory variables. Now that we've rejected the null hypothesis for our F-test, let's look at these individual slopes, beta sub 1 and beta sub 2. And this is the values that we find, negative 0.33 and negative 1, or positive 1.65. What do these mean? Well, it says for every 1 year increase in age, the mean estimated LDL value decreases by 0.331973 after adjusting for diastolic blood pressure. The beta sub 2 had 1.65133. That means for every 1 unit increase in the diastolic blood pressure, there is a change in the mean estimated value for the LDL cholesterol of 1.65133 after adjusting for age. So you always say after adjusting for the other variables. So let's look at the t-statistic for each of these individual coefficients. And what I want to write down here is you can write down all the 7 steps for a t-test. I'm going to skip some of those, and we're just going to calculate the value that we want from this. And if we look at the t-statistic, remember the t-statistic that is going to be, well, you take that specific, so that'll be a t-statistic for the ith, let's say then for the ith coefficient. Well, you take the coefficient value and you divide that by the standard error for that specific coefficient. And that is going to be described by a t-distribution on a certain degree of freedom under the null hypothesis. And we're going to say that nu, if we want to calculate nu, well, this is going to be n minus k. So remember, there's got to be a step number 1 where you say what is the population parameter of interest, and the population parameter of interest is beta sub 1, the change in the mean LDL value for every 1 unit increase in age after adjusting for diastolic blood pressure. Step number 2, we're going to have null and alternative hypothesis. Null hypothesis is that this beta sub 1 is 0. Alternative hypothesis, it's not 0. Remember, if that value is 0 in the population, well then age, no matter what you plug in, times 0 is 0, it's going to have no effect on the LDL cholesterol level. And that is, of course, after adjusting for the other explanatory variables. In the alternative hypothesis, we're going to say that beta sub 1 is not equal to 0. We're going to have a step 3, alpha equals 0.5. Step 5, we're going to have our assumptions for the use of this test. And we're going to say we're going to do a t-test because this we do calculate a t-statistic, and it is described by a t-distribution on n minus k degrees of freedom. And the assumptions, you can state all those assumptions. The one that we are going to just state here is that we have independence between all our variables, but there are many other assumptions as well, specifically when it comes to the residuals. We are going to calculate our t-statistic. So let's do that t-statistic for all of our values. What we do remember here is that our degrees of freedom, that's going to be 100 minus, we've got 3 parameters in our model, beta sub 0, beta sub 1, beta sub 2, and then so that's going to be 97 degrees of freedom. So let's look at t number 1, and if we do remember, what was that value? That was negative 0.331973 divided by its standard error, which was 0.619745. And that gives us about negative 0.5, check on your calculator, 3566, something like that. And we need to know the critical value. So, well, let's do that. Let me just show you where these numbers come from, so you're just clear about where these numbers come from. So if we look at the first t-statistic, you just take that value for that coefficient divided by its standard error. For t2, it's going to be this coefficient divided by its standard error. So let's do t2 as well. We are busy with it. Remember, its null hypothesis would also be that beta sub 2 in the population is 0. Alternative hypothesis, beta sub 2 is not equal to 0. So in this instance, it's going to be 1.65133. and we're going to divide that by 0.76005, and I get approximately, I think 2.16, somewhere there, 2.16424. Remember that is just going to be, well, let's put that there. Again, that's just going to be this, 1.65133 divided by 0.763005. And now for a step number 6, we need a critical value. That's going to be a t-value, and it's going to be on 97 degrees of freedom. And what we want is 1 minus alpha over 2, so 0.975 if you want to use software to do that. My critical value is 1.985, and we can see it's only this second t-statistic that is larger than. This first one is not. So in this instance, we're going to reject the null hypothesis, and remember, and I'll accept the alternative hypothesis. In this one, we're going to fail to reject the null hypothesis. Remember, under the null hypothesis, beta sub 1, not without the hat, this in the population at 0, for this one is equal to 0. And so that one we fail to reject, this one we reject. If you look at the results of a computer analysis, you'll usually then see the t-statistic right here, and you'll also see a p-value, and you'll also see, perhaps, depending on the software that we use, we are going to see confidence intervals around these coefficients. And so you can complete the table there. And so I would write a test conclusion, which I'm not going to do here. We're going to say that the age is not statistically significantly associated, linearly associated with the LDL after correction for with the diastolic blood pressure, and we're going to say that diastolic blood pressure is significantly associated, linearly associated with the LDL cholesterol in a model after correcting for age. So I hope that's clear, and it follows from just a t-statistic. In a follow-up question, you might be tasked with just calculating confidence intervals. So I do want to remind you how to calculate those confidence intervals. You take whatever coefficient you have, so I'm going to use a little I, plus or minus some confidence coefficient, and the confidence coefficient is going to be a t-statistic on degrees of freedom, comma, we want 1 minus alpha over 2, so 0.975 for that, and you multiply that by the standard error of that specific coefficient estimate. And so that's how we would calculate all of those. So let's have a quick look. While we have the page open, let's have a quick look at these. So the confidence interval for beta sub 1 hat, that's going to equal, well, we take beta sub 1 hat, which is negative 0.33197, plus or minus. Now, if you work out this, we have already done that. We know what the critical value is. We do have it here because that was the same value as for our critical value. That's how we had our critical value. And the critical value for our t-statistic, where did I write it? Oh, it's right there. 1.985. 1.985 times the standard error for this, and we do have the standard error for this. Remember, that comes from right there, 0.619, 0.619745, and so the values that I get for my lower bound, if I do the subtraction there, I get, I'm just going to do negative 1.56 all the way up to 0.90. And we clearly see that 0 is within that interval. And that absolutely ties with the fact that we failed to reject this null hypothesis. So guess what? If we calculate the confidence interval, 95% confidence interval, it is 95 because it's a 1 minus alpha confidence level. So if we look at beta sub 2 hat, that's going to be, I'm just going to take the statistic, that was 1.6, 51329, plus or minus 1.985, and that standard error was, what was that standard error? I think it was 0.63005, and now we will find that 0 should not be in this confidence interval. So if you do that calculation, I get 0.14 to 3.17. So clearly 0 is not within this, and that ties together with here, rejecting the null hypothesis and accepting the alternative hypothesis. Those go hand in hand. The final thing that you might be given in a problem like this is to calculate the r squared value. So I'm going to remind you the r squared, that's going to be the SSR, sum of squares due to the regression, divided by the total sum of squares. And if you plug that in, I get a value. Remember that just comes from here. There's my SSR divided by the SST, which is 97.232. So I get r squared. As I say, that's going to be 6550 and 0.265, and I divide that by 9797, what was that, 9797.232, and that gives me approximately 0.668. So we can express that as our model with these two explanatory variables explains 66.8% of the total variability in the low-density lipoprotein. Now we know that we've built in more than one explanatory variable, so what we actually want is the adjusted. We want to penalize for the fact that we've added more explanatory variables. So we want the adjusted coefficient of determination. That's going to be 1 minus, there's many ways, algebraic ways that you can express this, but it's n minus 1 times 1 minus r squared divided by n minus k. So we know what r squared is, we do have it there, we know n is 100, we know n is 100, we know k is 3. So if you plug in all those values, now it's going to be lower than this number, I get 0.6617. So this would be 66.2% versus 66.8%. So we would conclude that our model with these two explanatory variables explains 66.2% of the total variability in low-density lipoprotein. And in actual fact, that's not very good if your model can only explain 66. An r squared, we want to drive it up closer and closer to 1. So if you have many models to build because you have many explanatory variables, we would definitely try and build a model that has a better adjusted coefficient of determination. So let's have a look at this problem. It's going to be a problem on multiple linear regression. And so we're going to have a couple of explanatory variables and then a response variable, but remember our response variable must be continuous numerical. So in this problem, we are told that our response variable is low-density lipoprotein cholesterol measured in milligrams per deciliter. And we have these three explanatory variables. One is the age in years of our participants or subjects, the diastolic blood pressure in millimeters of mercury, and then a binary categorical variable, 0 or 1, where 0 is the normal diet and 1 is the test diet. And so we can imagine that these subjects were randomized to these two diets. And then what we want to know, or what we've decided here, is that our baseline is going to be the normal diet, and that this new test diet is going to be the one that's in our research question. So we are going to measure against this baseline of a normal diet. And we see the results here of our model. We see the intercept, the age, diastolic blood pressure, and diet. We see the coefficient estimates there, and we see the standard error for each one of these. So what we do have to remember from a table like this is that, remember, this is beta sub 0 hat through beta sub 3 hat. These are our coefficient estimates, and those are the standard error. And remember, if we do want a t-statistic, we're just going to take the coefficient divided by its standard error. Well, we also told then we had 100 subjects, and we see the sum of squares, or the total sum of squares, 9797.232, sum of squares due to the regression, 6550.376, and the sum of squares due to the error term, or the residual then, is 3246.856. So what I want to do is just to remind us how we calculate these. Remember the total sum of squares. Well, that says the following. Let's sum over all of these terms. And so that's going to be over each one of our subjects, 100 subjects. We're summing over I. That is that we take every value in the data set, the actual low-density lipoprotein cholesterol value, and we're going to subtract from that the mean of the low-density lipoprotein, and we square that. So we're just going to sum over all of these. And so you can remember that as the numerator of calculating the variance. So that gives us an idea of the variability in Y. How does it, every value in Y, every value in the low density lipoprotein variable, so you can think of that as a column in a spreadsheet, how does every value differ from its mean? If we look at the sum of squares due to the regression, we're going to take the sum also over all 100 of our subjects, and we're going to say, let's look at the difference between what our model will predict for that person minus the overall mean for that variable. And then the sum of squares due to the error term, we're also going to sum over all of those, but that's the difference between what the model predicts for the response variable minus what it actually is. So it's also going to go row by row for all 100 people, calculate the square of the difference between those two values and sum over all of those. So just as a reminder where these come from. So in step number one, we want to know what are the population parameters. Now the population parameters are beta sub 0, beta sub 1, beta sub 2, and beta sub 3. And we can describe each of these. Remember, beta sub 0, that would be in the population the value of the mean low density lipoprotein cholesterol levels for someone with an age of 0 diastolic blood pressure, and on the baseline of the diet. Now, of course, those are nonsensical as it stands, because we're really not going to have someone who's 0 years age and who has a diastolic blood pressure of 0. In step number 2, well, let's just say then beta sub 1, it's spoken about beta sub 0, but beta sub 1 is then, what for every 1 unit increase in age, how much does the mean of low density lipoprotein cholesterol increase or change, at least, after adjusting for all the other variables. And so it is for each one of these slopes, always adjusting for the other variables. So in our null hypothesis, we're just going to say that all coefficients, and by that I mean all those values, are 0. And my alternative hypothesis, at least one is not 0. What do we mean by that? It's much better to think about what this means. It means the null hypothesis, it says as a whole, these explanatory variables are not linearly associated with the low density lipoprotein. The alternative hypothesis, as the model stands, remember everything is adjusted for the presence of the other explanatory variables, that in this case, at least one of them is linearly associated with a low-density lipoprotein. At a very basic level, we can understand it as the null hypothesis. This is not a good model, and the alternative hypothesis that it is a good model. So let's do step number 3. And step number 3 says write the level of significance, and that's going to be 0.05 or 0.05. Step number 4 is what test are we going to use? Well, we're going to use analysis of variance, so we're going to conduct an F-test. And what are the assumptions for the use of that test? Well, I'm not going to write all of those down, but we do know we need a linear relationship between our explanatory variables and the response variable. We need that all these 100 subjects are independent, so all our observations have to be independent. We also need homoscedasticity, and what that means is when we are done and we look at the variance of the error term. Remember, there's the error term, the difference between what our model says the estimate of the low density lipoprotein level should be and what it really is for each subject. That across all the values of our predictive variables that we have a constant variance of these error terms. And then we also want the error terms to be normally distributed. So we only mention these, but we don't go to any detail when it comes to this introductory course. So we're going to use an F statistic, and we need to know how to calculate this F statistic. And so let's go to step number 5. And let's use a green pen. And we're going to say that F statistic, how do we calculate that? Well, we take the sum of squares due to the regression, and we're going to divide that by the numerator degrees of freedom. And then we're going to divide all of this by the sum of squares due to the error term, and that is divided by the denominator degrees of freedom. You would also see this in some textbooks as the mean squared due to the residual, the numerator, and this is the mean squared error. And so those are the two terms that you might see. And remember, this is described by this f if I were to just have the null hypothesis, and from such a population I repeatedly, or I do my study repeatedly every time I get different values. Here I'm going to calculate a different f statistic every time due to variability, but the distribution of this, all these f statistics, that is going to follow at least an f distribution on two parameters: the numerator degrees of freedom, the denominator degree of freedom, that is if the null hypothesis is true. That's what I'm going to see. I also just have to remember how to calculate the numerator degree of freedom. This is going to be k minus 1, where k, remember, is the number of parameters in my model. And I have 1, 2, 3, 4 parameters in my model. And I also have the denominator degree of freedom. That's going to be how many subjects were my study minus the number of parameters in my model. That would be the easiest way to calculate this for this case. So in step number 6, let's calculate this f statistic. And so you've got to plug in those values. So for the sum of squares due to the residual, that was 6550.376. And I'm going to divide that by 4 minus 1. I have 4 parameters, minus 1 leaves me with 3. And all of that is divided by the SSE, which was, I think, 3246.856. And that has got to be divided by 100 minus 4, which is 96. And that gives me about, check on your calculator, I get about 64.56. 64.56. That's a very big F statistic. Okay, so if we had to look at a critical value, so that's going to be a critical value on 3,96, and then 1 minus alpha, which is 0.95. If I look that up using software or spreadsheet software, I get a critical value of 2.699. And so that we have that our F is much larger than this critical value. As a consequence, we are going to reject the null hypothesis, and we're going to accept the alternative hypothesis. And so if we write the test conclusion, so I've written simply, there's enough evidence in the data at the 5% level of significance to show that at least one of the explanatory variables is linearly associated with the LDL cholesterol values. But in a more basic sense, I can just think that this model shows a significant linear association between these variables as a whole as predictors of our explanatory variable. But now we have to go one step further, and now that we've rejected this null hypothesis, now we can look at the individual. We can look at the individual coefficients. And with a model like this, remember, we don't really care about the intercept, because that would just mean that age, diastolic blood pressure, and diet, they're all 0. And at least for age and diastolic blood pressure, remember, a linear model is only valid, on the interval in which we have data. And certainly, I don't think in this data set we would have someone who's 0 years old and who has a diastolic blood pressure of 0. If you have a diastolic blood pressure of 0, of course, that signifies loss of life. So that's kind of nonsensical. And so we don't care in a model like this really about understanding the intercept. What we understand is looking at these individually now. So let's have a look at all three of them together. If we look at a hypothesis testing there, we're going to have step 1. And in step 1, again, the parameters of interest are going to be beta sub 1, beta sub 2, and beta sub 3. And so those are our coefficients. Now, coefficients, remember, that would say for every 1 unit increase in age, we see a change in the mean LDL level of this much after adjusting for diastolic blood pressure and diet. And the same for those other two. So those would really be the parameters. In step number 2, we're going to write a null hypothesis and an alternative hypothesis, and we've got to write that for each one of these. So if I can just do them all on one line, I'm going to say that beta sub 1 equals 0, and beta sub 1 is not equal to 0. Let's write them all like this. And for the next one, I'm going to say beta sub 2 equals 0, and beta sub 2 is not equal to 0. and h sub 0 for our final coefficient, I'm going to say that beta sub 3 equals 0, and for the alternative hypothesis there, beta sub 3 is not equal to 0. So what does it mean under the null hypothesis? Now, if you multiply anything by 0, it's just 0, meaning it doesn't matter how you change the age, it's going to have no effect on the LDL cholesterol. Same here, if you plug in a 0 for beta sub 2 in a model, and you multiply that by any diastolic blood pressure, that's still 0, so no matter what happens to the blood pressure, it's going to have 0 effect on LDL, and the same here for the type of diet that someone is in. Now, that's the test diet compared to the baseline, which is a normal diet. So we've got to do 3 of these hypothesis tests. So step number 3 is going to be our alpha value, and we're going to set that to 0.05. And step number 4, well, what test are we going to use? Well, we're going to use a t-test. We're going to use a simple t-test. And the assumptions for the use of that test, once again, are like we had before. So we're really talking about the independence and everything else as far as these models are concerned, which we don't cover in an introductory course. We're going to assume that the assumptions for the use of this t-test are met. Most notably, we're going to say that there is this linear relationship between these explanatory variables and the response variable, and that these observations are independent of each other. So if we look at step number 5, we can actually show how we calculate this t-statistic. We're going to say that the t-statistic is going to be this coefficient. Now we're going to do that for one specific coefficient. So we take that coefficient value that we have, and we can also say minus what it is under the null hypothesis. So we're going to say beta I under the null hypothesis, but that's 0. And we're going to divide that by the standard error. We're going to divide that by the standard error of that specific coefficient. And we're going to say that if we, under the null hypothesis, if we were to do this over and over again, we're going to get a distribution of t-values, and that's going to be a t-distribution on some specific degree of freedom. And remember, that's under the null hypothesis. And if we want to look at how to calculate all these degrees of freedom, that's n minus k, where that's our sample size, and that's the number of parameters in our model. Now, do remember how we calculate all of these. It's just this value, the coefficient, divided by its standard error. Coefficient divided by its standard error, coefficient divided by its standard error. So let's have a look at those. So if I look at my first t-statistic, it's going to be that negative 0.3, what was it, 0.322458, and I'm going to divide it by its standard error, which was 0.644801, and then I get approximately negative 0.05, which is a small t-statistic. Let's look at the t-statistic for our second coefficient. That is going to be 1.6, what was it, 3069, and we're going to divide that by 0.84763, and I get roughly 1.9238. And then for our third t-statistic, we're going to get 0.13576. And we are going to divide that by, what was that, 2.37452, and that gives me approximately a small value, 0.0572. If I now look at a critical value, that will be a t-statistic on 96 degrees of freedom, and I want 1 minus alpha divided by 2, so that'll be 0.975. And that is going to be about 1.985. And if we look at each one of these t-values, we're going to have that t1 is not larger than our critical value. It's negative 0.5. We take the absolute value of that. Remember, this is a two-tailed alternative hypothesis, so our critical value is negative 1.9, positive 1.985. Definitely 0 is in that middle region, failed to reject. T2 is also not bigger than our critical value. And if we look at T3, surprisingly, that's also not bigger than our critical value. So our conclusion in all 3 of these is fail to reject the null hypothesis. failed to reject, failed to reject. So, that is certainly possible. If we looked at our F-test, well, we rejected the null hypothesis, and that said at least one of them are. But what we see with a test like that, and that's why I sort of want to emphasize the basic understanding of this F-test. It says this model as a whole shows us that there's a statistically significant difference, in a real sort of baseline way of looking at this, non-scientifically, perhaps would be the null hypothesis is that this is not a good model, alternative hypothesis that in combination this is a good model, and it turns out it is. But if we look at the individual coefficients, we see that none of them actually are significant. We can perhaps see that this one gets very close, so that's just going to be for p-value just over 0.05. But certainly, remember, these are all adjusted for each other, and if we look at them individually, none of them are linearly associated with the LDL cholesterol value. And so certainly a model like this is completely possible. So if I were to write step number 7, my conclusion, I would then write, I'm not going to write it, I'll leave that to you, that you would write for each one of these, you would say there's not enough evidence at the 5% level of significance to show that, then first of all, age is linearly associated with LDL cholesterol level after adjusting for the other variables, and you would go through each one of those. So in the next step, we might be in the next type of question to say, well, can we calculate the 95% confidence intervals? And those must support the conclusions that we reached here, that for each of the 3 intervals, we should not find 0 in any of those intervals. So let's just remind ourselves how to calculate the confidence interval for some specific one of these coefficient estimates. So I'll put a little I there, is you take that coefficient estimate and you say plus or minus some coefficient, some confidence coefficient, and this will be t on a certain degree of freedom, and 1 minus alpha over 2 as far as our confidence coefficient here is concerned, times the standard error of that specific coefficient. That's specific, so let's put a little I there. So if we'll have a look at the 95% confidence interval for beta sub 1 hat, now that is going to be beta sub 1 hat, which was negative 0.32246 plus or minus, that is the same, remember that is the t on degrees of freedom was 96, comma 1 minus alpha over 5 leaves me with 0.975. So if you want to use software, those are the values that you would require, and that is just our critical value that we have there. So it's 1.985 times the standard error. Now the standard error for beta sub 1 hat, remember we have it right there. There's our standard error, 0.6448. And then I get confidence levels of negative 1.6 to positive 0.957. So certainly 0 is in this interval. So we're 95% confident that 0 is in this interval, and hence we could come to the same conclusion there. We failed to reject the null hypothesis for that coefficient. If we look at the confidence interval for beta sub 2 hat, remember I'm just going to plug in beta sub 2 hat, which was 1.63069, plus or minus my confidence coefficient, which is 1.985, times the standard error, which was 0.84763, and then I get all the way from negative 0.052 to a positive value 3.313. Check if see if you do see the same, and that one was close, and that's why that was almost beyond our critical value, but certainly 0 is still in that interval, so failed to reject the null hypothesis. If I look at my final one, beta sub 3 hat, and beta sub 3 hat was, what was that, 0.13576 plus or minus 1.985. Remember that if I multiply these two, that's my margin of error, margin of error, margin of error, and I multiply that by the standard error, which was 2.37452, I get again from negative 4.578 all the way to positive 4.849. So again, 0 is within that interval, and hence the same thing there, failed to reject the null hypothesis. Good, then in the next question you might be say, well, use your model to calculate the mean estimated low-density lipocholesterol level, low-density lipoprotein cholesterol level. For someone who is 55 years old, with a 90 millimeters mercury diastolic blood pressure and who was on the test diet. So if they're on the test diet, that means we plug in a value of 1 for that person. So we're going to write down our model, which was negative 44.1804 minus 0.32246. That's the coefficient beta sub 1. And that's going to be times the 55-year-old age. And then plus, I think our model had 1.63069 times the 90 when it comes to our diastolic blood pressure, plus a 0.13576 times 1 for our test diet, not 0 because that would be someone on a normal diet. And I get a mean estimated LDL level of 84.98, and that'll be in milligrams per deciliter. So you've got to think about what are these, what are the units of these coefficients. And so if you want to end up there, and that's in years, you'll have to think what is the units of each one of these. And that's a bit of fun. You can work that out. In a final part, we might need to calculate the R-squared value and the adjusted R-squared value. So let's write that R-squared, or the coefficient of determination. That's going to be the SSR, the sum of squares due to the regression, divided by the total sum of squares. And if we do that, in our instance, I get 0.6686. 0.6686. So we could say that our model explains 66.86% of the total variability in low-density lipoprotein levels. And remember, I just get that from here. Where did it go? There I get it. SSR 6550 divided by SST 9797.232. This one divided by that one. But now I need to do the adjusted R-squared because I've got more than one. So I'm going to do, the adjusted coefficient of determination. That's 1 minus, there are various algebraic ways to calculate this. N minus 1, 1 minus R squared, divided by N minus K. And we've got all these values. We're plugging in 100, 100. We're plugging in a 4 there because we have 4 parameters in our model. And if you plug all those values in, I get 0.6582, which will always be smaller because I'm penalizing for the number of explanatory variables that I have. And in the end, I'm going to say my model explains only 65.82% of the total variability. And that means just under 35% of the total variability is left unexplained by my model. That's quite a bit. We want a model with a very high R-squared level. That would be ideal. So I've opened ChatGPT. I'm using the O3 mini high model, as you can see here. And here's my prompt taken from our problem. So I said, help me resolve the following biostatistics example problem. Researchers collected data on the age in years, diastolic blood pressure in millimeters of mercury, the diet type, and then I write in parentheses, subjects were randomized to a normal diet or a new test diet, and then finally their low density lipoprotein levels in milligrams per deciliter. They build a linear regression model with age, diastolic blood pressure, and diet, and then we're using the normal diet as our baseline category as explanatory variables and the LDL value as their response variable. From a sample size of 100 subjects, the coefficient estimates and the respective standard errors are as follows. I've typed those in, and that comes exactly from the problem, as you can see. Then I also wrote the total sum of squares, the sum of squares due to the regression, and the residual or error sum of squares, SSE. I write all those values in. And then finally, the researchers want to determine if this is a good model at the 5% level of significance using analysis of variance. Create a solution using the following steps, and there I've listed our 7 steps. And this is the thinking model. So it thought for a while, and we see the population parameters there as we expect, beta sub 0 through beta sub 3. And without the hats, remember these are population parameters, and they are described there. It's those, the intercept and the 3 slopes. We see our null hypothesis that all these values are 0, all 3 slopes. Alternative hypothesis that at least one of them is not 0. We see a significance level of 0.05. We see that we can use an F-test for overall regression significance, also known as analysis of variance or ANOVA, the ANOVA or F-test. We have our assumptions there that I mentioned: linearity, independence, homoscedasticity, and normality. We calculate that F statistic. As you can see here, ChatGPT used the mean squared due to the regression and mean squared error, which is just the numerator and denominator of our F test, and the numerator is then the SSR. Just be mindful of the K and the N minus K minus 1. So it uses a slightly different algebraic form, where K here is the number of predictors, whereby we usually use the number of parameters in our model. It's still going to come to the same two degrees of freedom, because 4 minus 1 is 3 and 100 minus 4 is 96. So we still see the 3 and 96. So there we go. We see the numerator, which is SSR, then divided by what we would call K minus 1, and the MSE, the mean squared error, which we would call the SSE, divided by N minus K. And you get exactly the same values. If we take that ratio, which is called the F statistic or the F ratio, it gets 64.45 as we did. And remember, that is on 3 and 96 degrees of freedom. So if it calculates the critical value, it also gets about 2.7. That's fine. And we reject the null hypothesis with the test conclusion, as you can see there. So that worked very well. And then I said, next, now help me with the next question. This problem research have rejected the null hypothesis and accepted the alternative hypothesis of the F test, perform hypothesis testing for each of the coefficients for the age, diastolic blood pressure, and the diet type explanatory variables. And ChatGPT reminds us how to calculate the T statistic. It's just going to be that coefficient estimate divided by its own standard error. And the degrees of freedom, it uses the N minus K minus 1, but its K, remember, is not the same as ours. Ours would be N minus K, the sample size minus the number of parameters, and we get to the same result, 96. And so we need to test all of them. Individually, we're going to say that each one of these betas are 0 under null hypothesis and 1 under the alternative hypothesis. And then it's a simple question of taking every coefficient, dividing by its own standard error. And we see the 3 T statistics there as exactly the same as we calculated. And then in the end, none of them are larger than the critical value, or at least in those regions of rejection. And we failed to reject any of those null hypotheses with the final summary there. And it states there, thus, when performing individual hypothesis tests for explanatory variables, none of the coefficients for age, diastolic blood pressure, or diet type are statistically significant at the 5% level of significance, even though the overall F test indicated the model itself was statistically significant. This suggests that while the variables together explain a significant proportion of the variability in LDL, none of them individually show strong evidence of an effect on the conventional significant level of 0.05. The confidence intervals exactly there as we had them, and again then on 96 degrees of freedom, and we see the lower and the upper value. We also see it for the intercept, which we do not really care about, but look at that for each one of those, negative 1.6 to 0.95. So again, 0 is in that interval, 0 is within the interval for diastolic blood pressure, and 0 is within the interval for the new test diet, negative 4.57 up till 4.84. So again, that is just the same conclusion we must reach, because we are using a 95% confidence interval and we're using a 5% level of significance. So we must come to the same conclusions. Then we had the idea of someone who's 55 years old with a 90 millimeters of mercury diastolic blood pressure who's on the new test diet. We simply plug those in. You can see the model there, beta sub 0 plus beta sub 1, etc. And it should put the little hats on top of those betas, actually. I think you should do that, absolutely. But we get to the same result, about 84.98 milligrams per deciliter. That's the mean estimated LDL level. And then finally, the coefficient of determination, also SSR divided by SST. And we also see the adjusted R squared there. It's exactly the same solution as we come to. Remember, the K that ChatGPT uses is not the same K that we use, but the results are exactly the same, 0.658. So it says there, with the adjusted R squared, after adjusting for the number of predictors and the degrees of freedom, the model explains about 65.8% of the variation in the LDL cholesterol levels. The adjusted R squared is slightly lower than the unadjusted R squared, reflecting the penalty for including additional predictors that do not improve the model substantially. And that is, I think, a very good way. ChatGPT once again has set the solutions out very nicely, and I urge you to use it yourself.